So in today's video we're going to be looking at the DB04R remote controls because there's a couple that you'll find that are available from different sellers, and now there's an official remote control that DB04R Happiness Fireworks System presents with their products. So the first one is the one that you're probably more familiar with in front of me. It's the 1 to 12 button remote. It's a general purpose remote control which is obviously used for lots of other devices, but they use this also for the firing system as part of an ease, is my guess. The only awkward thing about these remotes, which often gets commented on, is the fact it uses a very small 12-volt battery on the back, which is very difficult to get hold of in certain areas of the country, or in the world, I guess. It's not a common battery, and I've certainly struggled in the past to get hold of one. So that's always been an issue with these remotes. But then after they did the blue one, they then did a grey remote. Now this is the first one that Happiness actually sort of started to, what would you say, take some independence off the previous ones, because now they've got their own graphic overlay and they've also added a switch to the sides, unlike this module that doesn't have a switch. So as soon as the battery's in it, you can potentially fire anything that's on, whereas this one you have a separate switch. Now interestingly, when they did a teardown of this module, you would find that actually that switch placement is also on this circuit board, so you could modify an older remote without a switch to have a switch. It's not that difficult. Now lastly is their new remote, this one. So this one has a couple of interesting features. So let's go to the other two and have a look at this one on its own. First of all, it runs on a 9-volt battery rather than a 12-volt battery. Now some people have asked, well, why do we need a 12-volt battery or a 9-volt battery? Can we not run this off AA batteries, for example? And that is very difficult to answer, because this is the reason why they're using such a high voltage is because of the transmitting side of the circuitry. So if you just simplify RF into just standard electronics, as you're probably used to, then output power is going to be dictated by V times I. So the higher the voltage you have, technically the better you're going to end up transmitting. It'll end up transmitting further because you've got a higher voltage to start with, and then obviously you just limit the current on your wattage. So that's the reason why they use a higher voltage than the standard AA batteries. That's my belief why they use a higher standard. Now on this remote, we've now got a power switch on the side that when we turn it on, you'll be able to see we get a red power light on top that tells the controller's on. Pressing the buttons, you'll see, I don't know if you can see it on camera, but the light flashes. And down here, we've now got the all fire button and the sequence fire button. These are the two special features which the other controls can get to if you use binary, but that's over the 13, 14 and 15 numbers, which the other remotes don't have. But now if you hold down the all fire button, for example, can you see there's a short period when it goes off, so it waits and then it starts firing. So you get a 1 second or 2 second delay. I can't remember how it is. I think it's 1 second too, but obviously 2 seconds. And then the same for the sequence. So they now include these delays and the special function features, which for me tells me this is going to be a microcontroller based system inside to get that delay, because the original chipsets don't have that delay. Right, without further ado, we'll move on to the actual PCB and I'll break that down for you, and then we'll look at the actual circuit schematic. So this is the front side of the PCB, and that's the back side of the PCB. So you can see the back side only has looks like a microcontroller, a capacitor and a couple of inductors, so not that particularly interesting. So let's first of all analyze the front side. Now when I look at a PCB to start understanding it, I look for blocks, because a lot of professional PCB designers will design PCBs in functional blocks because that's just the best way of doing it. It makes it much easier to look at, to read, and for other designers to be able to analyze, etc. And then when you come to debugging it, for example, it just becomes much easier because everything's where it should be and there's no random components around the place. So let me just first of all start off by drawing where I think the blocks are. So down here, this bit down here looks to me like a block. This bit over here with the switch looks to me like a block. This bit down here in the middle looks to me like a block. This capacitor here is obviously just some smoothing, possibly, or decoupling on the other side of the board. They decided to put it this side for some strange reason. Then up here, that looks like a block. And then you've got switches and that around. So now I know the blocks, I can begin to think about how this is going to function. So this block on the left-hand side, it has the tin can in it that says R 433, but that's obviously going to be a 77 frequency because that's a general use frequency is 433 point something. And then that goes to a rather large component that's going to be a high power component, so that sort of shouts transistor amplifier to me, and it also connects to the antenna. So let's actually now go through how I would now actually reverse engineer this. So I would go from a power line, so let's go from the positive rail here, and I'm just going to follow that rail all the way around the board. So first of all, it comes up here, it goes to this capacitor, and then goes through under this resonator into this transistor. That transistor output goes to this antenna. So now this shows me this is obviously the RF section. The power rail continues over here, it goes under the board, there's an inductor we know about on the other side, and then it goes up here, it goes through these one side of these capacitors up to this component here. LR5 is often going to be a voltage regulator, and we know it's going to be a voltage regulator because of the smoothing capacitors as well. Generally around regulators you'll find there'll be an awful lot of smoothing capacitors, and that works out really well here. You can see we've got lots of capacitors. Then that goes up here to this diode, down through the switch, back in to maybe a plane of some sort. Now the output of the regulators, this is now the next power plane, if you like. So we've done the 9 volts, we followed the 9 volts around the board. Now we're going to follow the 5 volts, and the 5 volts really easily comes out of the regulator, and then it goes down over here to these wires here, and it also goes down off that way. So this is really simple. It obviously looks to me like it's going to go to the microcontroller. So we've got the RF section down here, we've got the power section over here, and then we've got the power section for the microcontroller. Over here we've got an LED and a resistor, so that's obviously just the actual light on the top of the module. Now this middle section here, this is the interesting part, because we've got these 2 transistors here that don't seem to really go anywhere. And if we look at how they're wired, that might. So first thing I was thinking is, could these be diodes? Because we've seen in often everything else that the Happiness Company do, they generally use diode forwarding, or what's called as diode steering, sorry, to take like the switch inputs into binary. So they create the switch inputs into binary, which makes 4 effectively inputs needed on the microcontroller. So I thought, could this be diode steering? And the answer is, well, no, because A, there's not enough diodes, and B, these 2 resistors up here give you a really good clue to what this could be doing. So what I would say is, if you look at this in terms of sort of what functions is left to do on this controller, that's the awkward part, because you think, well, you've got the radio section, you've got the power section, you've got the LED, you've got the switches. What is left to do? And for me, the answer must be in the RF section, because we know that this is using a technique where you just basically send spurts of a carrier. There's no data. That's why if you look on the RF section, it goes directly from the carrier to the amplifier. There's no modulator or a mixer, because you're not putting the data in. All you're doing is you're sending the spurts of the RF, and if it's a long spurt, then that will be a 1. If it's a short spurt, that will be a 0. So the microcontroller must be controlling the amplifier for the RF, and it's the amplifier that's turning it off and on, which is giving those signals. And we know that the microcontroller will only be able to source, a couple of milliamps, maybe 20 milliamps at maximum if you really desperately want to push it. So we need enough current to be able to enable the transistor, the power amplifier transistor, fully. And once we know that, it becomes obvious what these components are here, because we have a resistor here, which is obviously a current limiting resistor. That goes to this resistor here, which is connected to ground, and then it connects to the first pin of that SOT. So we've got a current limiting resistor, a biasing resistor to ground to hold whatever this is low unless it gets a signal. So this must be the base of a transistor. If that's the base, then we obviously know that this here is going to be the emitter, and that connects to the base of the next one, and then that emitter connects to ground. The 2 collectors connect together and then go through a wire on the other side to the board. So those of you familiar with your basic circuits will see that this is obviously a Darlington pair, and a Darlington pair has the advantage that it's basically allows a smaller current transistor or device to drive a much larger current device. So we've got a Darlington pair. Okay, that really sums up the board. We'll move on to the circuit diagram. Okay, so let's look at the schematic next. We have formatted this schematic like how you should format a schematic. So we've got inputs on the left, processing down the middle, output on the right. So very first, far left, we have our power input. So our 9-volt power rail goes into an inductor, through the power switch, through a diode, a reverse protection diode, which is a nice design, just to stop you from flipping the 9-volt battery the wrong way around and then destroying the circuit. And you may question what the inductor is there for. Well, I've had a look myself, and for me, I think this is probably because of all of the RF stuff being unshielded and so close to the power rails. Maybe they were concerned that, or maybe they found there was some AC leakage into the DC rail, so they put the inductor there to try and quell that, maybe. After you go from the power switch and the diode, you go into the voltage regulator. Again, we saw that in the board with all the capacitors down it. That's just a standard 5-volt regulator. I have to confess, I can't find an awful lot of details about it, so I guess that's one of those generic ones that they're using in Chinese manufacture. The other input side of this is, of course, the switch matrix, and the switch matrix was a slight surprise to me, even though we did see on the PCB that there was no diode steering, because a lot of the previous stuff we've torn down from the Happiness used diode steering to lower the input numbers, input port numbers for the microcontroller. In this case, they're using a far more standard system of using a switch matrix. And for those that are unaware how a switch matrix works, it's really, really easy. What you do first is you effectively make all your columns, well, it'd be good to make them high impedance if you could, or low if your controller doesn't allow that. Then you basically make first one high, so column 1 goes high on one edge of these switches. Then you scan the rows. So if, for example, I press switch 4, row 2 would be high at this point in the time. So we'd know that switch 4 was pressed. Any of the other switches on any of the columns wouldn't do anything. So then once I've scanned column 1, I put column 1 low again and put column 2 high. I rescan all the rows. Once I've done that, I then put column 2 low, column 3 high. I rescan all the rows again. So you see you've got this constant sequence of events, and by knowing which column is high and which row is high, you can work out which switch is effectively pressed. And this is what I assumed they were doing, but I was absolutely wrong about this in some ways, because if we now look at the button pushes, so this is a capture of the button presses. So this bit beforehand, you can see where they've got all the columns high, all the rows are low. And this state of all the columns high, all the rows low is a continuous state. This is the preamble state, if you like. So this is before you've pressed the button. It doesn't change. This is the set state. When you press the button, that's when things change. And that tells me this is not like a continual loop. This is an interrupt-driven process, which is interesting because if you drive it by an interrupt, you can go into sleep modes and things like that and get low power modes. However, we'll see if they do that later on. Let's have a quick look at this then. So if we look here, for example, button 5 I've pressed here. So if we just have a quick look at the schematic to find out where button 5 is, button 5 is on column 2, row 2. So if you now go back, we'll see that column 2, row 2, can you see that you've got this pattern where suddenly where you've pressed the button, column 2's gone low and then gone high again. As you see, they rescan to see as they're trying to detect that button. The button's obviously triggered an interrupt, but they're not quite sure where that button is yet. So maybe they've put an interrupt across all the rows or something that just fires to say something has happened, and then they rescan. And you can see that the process of how they're rescanning. And what's interesting to look at is that the two graphs here on column 2 and row 2, you've got that 2 spike pattern compared to the others that only have 1. So you can see where you're pulling it low and we're pulling it high and how it's getting triggered. And every so often they repeat that. So if you look at the column 2, can you see that's the length of the button press over that point? Can I put my markers on? So if you look there across to there, that is the length of time I pressed the button because it's constantly pulling column 2 low. but in the middle of these things, you can see where it's re-scanning and rechecking to see if column 2, if that button has been released or still pushed, and figuring out which button has been pushed. So they're doing an interrupt-driven system rather than a constant loop, and then rechecking every so often. And if you look at, for example, you can do this again, look at button 1, for example. So button 1, you can see, look, column 1 goes low. And then if we zoom in a bit more, we can see row 1 gets that pattern, those two little humps. So if we go look at the schematic, switch 1 is in column 1, row 1. So we should get that on the schematic, column 1, row 1. We do. So there we go. So you can see how we're doing it. You can see how they're doing it. What is interesting is when you get to the arm and the sequential button, because on those buttons they change it, because you've got to hold it for 2 seconds. They don't just resample it after like 30 seconds. They continually sample it. You've got to hold that button continuously for 2 seconds. If you let go, it will reset. And this is what you'll get. You'll get this very interesting graph where they're constantly re-scanning the keypad matrix to constantly see that you're constantly pushing that button. Now, after the 2 seconds is up, if we look, you'll discover, well, it's not quite 2 seconds, is it? It's 600 milliseconds or something like that. After that is up, you'll see that it's probably 1 second, because maybe that's when they try the next one here. You can see it rescans every so often to see if you're still pressing the button for it to keep sending the all fire signal, but it doesn't hold that delay again. Once you've held it for that length of time, it sort of times out, and doesn't matter how long you hold it thereafter, it will just do that singular scan round. It won't wait for another second or 2 seconds or whatever it ends up being, 800 milliseconds, before the next one hits. So let's go back to our schematic and carry on going around. So the middle of our schematic is obviously the microcontroller, and you can see where I've labelled how it works. So pin 4 is obviously the power for it, and they've got a decoupling capacitor for pin 4. Pin 11 is obviously the ground. Pin 14 is the LED at the top, which they drive again. It's a soft LED, so it's not just on the power rail, it's actually being driven by the microcontroller. And you can tell that because when you press the button, it actually flashes when you send the transmit. So they're obviously making you aware that that's what's happening, you're transmitting something. And then on pin 8 is the driver for the Rf Amplifier. And we'll see that next. So here is the circuitry for the Rf Amplifier. Pretty standard in some ways. So you can see you've got the resonator, which is creating the 433 megahertz, and then that's what you'd normally have. If you look at like a standard radio, you'd have input frequency, input filtering, then you'd have some sort of mixer modulator, then you'd have amplifier, then you'd have your output filtering, then you'd have your antenna. It's a very basic system. On this one, you've basically just got your carrier that goes straight to your antenna, and there's a little bit of output filtering, but that's driven by this transistor here. This transistor here is that large one you saw on the board by the RF antenna. But what is interesting here is if you look at the grounds. So you've got ground, what I've called ground A, or ground analog in this case, and that is not connected to ground right now. That is connected to those Darlington pair transistors. So here we go. This is our, do you remember those two resistors I showed you on the PCB? That was connecting to these two Darlingtons. That's going from this Darlington pair, sorry, that's going from the microcontroller, and then these two Darlingtons are connecting the analog ground to actual ground. So that means that why these transistors are not actually enabled, this whole circuitry is floating. So that means it's not working at all. That's what's disconnecting it. So it's only when that ground gets connected to, when analog ground gets connected to real ground, will this start doing something. Other than that, it's just floating there, doing absolutely nothing. Now, the issues with anything like this is you've got fast switching and you've got high current, which means you're going to get massive disturbances on the voltage rail. So you can see more why they've got a lot more capacitance in there maybe than you'd normally put in, because they're so concerned probably about driving the power rail into a lower voltage, which may then upset other devices, particularly the microcontroller. These days microcontrollers aren't too bad, but it used to be that if you drove a microcontroller, like if you kept dipping its power rail, you would discover that it would start to misfunction. Let's now have a quick look at the outputs, because you should see this will look so familiar to the last remote control one I did, the white remote control, because it's exactly the same frequency. It's actually the same, codes. It's a binary code system, Every button has a number, a binary number, and that's what's basically being transmitted. And it's doing it in spurts of RF. As I was saying in the PCB, it does a long spurt for a 1 and a short spurt for a 0. The receiver knows something's going to happen because there's a preamble and a fixed time length, and then it sends the data. And the data is sent first of all by the unique code, 19-bit unique code. That's the identifier of the remote itself. That should be unique to that remote. However, how unique it is up for discussion. And then you've got the data, the 4 bits of data at the end. It's exactly the same as you've seen in previous videos. This remote is doing nothing clever other than on the arm and the sequence, it's waiting for you to hold it for a long time before it sends it. Something else which is quite interesting is I think on the generation 1 or the false generation 1 that I did a teardown of, I think 12 was the all fire and 15 was the sequence fire, whereas they've got 13 and 15 on this remote as the special functions. So let's have a quick look at some oscilloscope traces. This is the last thing because we might as well have a look at some. So this is the trace of the controller transmitting. We've got the power rail on the yellow trace and then current showing on the blue trace. And yes, you can see, look, when you're transmitting, you're getting dips in the power rail. However, look, it's only about 0.4, 0.5 volts at maximum, so that's not going to worry anything particularly. That'll be fine. What's also interesting, if you look just at the current traces, you can actually see the code it's transmitting through the amount of current it's taking in pulses. So if you were to look at this on the transmitter, you would see that as 0, 0, 0, 0, 0, 0, 1, 0. Do you think you can see by the actual current pulls what the actual transmission pattern is? And this is quite clever because you'll find lots of times when you're reverse engineering something, you can tell an awful lot by the current pulses. And this is part of reverse engineering, is you can actually study the current pulses to figure out how the circuit is operating. More complicated pieces of equipment will go further. If you're looking at, for example, like a safe, electronic safe, they will deliberately disguise the way they draw current in a safe to stop you from realizing things like how to figure out the code, etc., from looking at the current. Lastly, this trace is standby. So this is the remote turned on but not transmitting, and you can see, we've got 40 milliamps of draw here. This is awful for a battery-powered device. You would expect nanoamps if you're in a more modern device. Some of this is going to be that LED that always stays on, but that's only going to be a couple of milliamps probably at most. So I'm not quite sure why their current draw is so high. Their microcontroller must be really drawing something here. I suspect they've got lots of clocks and so forth running, as in the internal registers running, because quite often in microcontrollers, the more you turn off in the internal registers, the lower power you'll get. So there's lots of different watchdog timers and that you can remove, and brownout timers, etc. So there we go. I hope that is interesting. That has been the DBR06 remote. I will be doing a few other videos later on, hopefully this month, probably next month now, of returning to the DBR04 memory allocations, because I found that when I brought this remote, the special functions do not work, and I'll describe why that's the case, and then I'll show you why and how we can get them working. I might also have a Pi Pico project that I'll show you, because it's one of those projects which has just been absolutely endlessly in terms of the amount of issues I've had with it, and you'll see how I've had to overcome these things. But anyway, I hope that's been helpful, and I'll see you next time.